Hey everyone, we are Tanishq and Soham, and this is GAZE, Generalizable Anemia Detection via Conjunctival Zone Examination. This is our final project for CSCI 5922 at CU Boulder. Let's get into it. The problem: anemia affects 2 billion people globally, and most of them are in low and middle income countries where getting a blood test just isn't possible. But here's the thing: anemia leaves a visible physical marker. The inner lining of your lower eyelid loses its pink color as hemoglobin drops. A smartphone camera can potentially detect that. The gap we are targeting is that prior models were never actually tested across different populations. The 98% problem. This is what motivated our project. Ramos Soto et al. Reported 98.47% accuracy using Vision Transformer on the Eyes Defy Anemia dataset, which contains both Italian and Indian patients. An impressive number, but they merged both populations into one dataset and never asked, does this model actually work if you train on one population and test on another? That's the question nobody answered, and that's exactly what we set out to test. Our approach? Our setup is straightforward. We used Eyes Defy Anemia dataset, which has 122 Italian patients from Bari and 95 Indian patients from Chennai. Instead of merging them, we created three explicit splits: a merged baseline to replicate prior work, IT to IN, where we train Italian and test on Indian, and IN to IT, the reverse. We evaluated three architectures: ResNet 50, EfficientNet B0, and VIT base under two augmentation conditions. Condition 1 uses just flips, matching Ramos Soto. Condition 2 adds color jitter and brightness shifts to simulate demographic variations in skin tone and lighting. The result table. Here's what we found. The merged baseline performs reasonably. EfficientNet hits F1 of 0.698, VIT hits 0.75, but the moment we go cross demographic, things break down fast. IT to IN partially works. VIT with domain adaptive augmentation hits 0.834 F1. That's actually strong, but IN to IT, every single model collapses. F1 scores between 0.17 and 0.27, with recall of 1, meaning the model just predicted everyone as anemic. That's class collapse, not generalization.
The headline findings in this asymmetry, Italian to India is 0.834 F1 score and India to Italian is 0.272. And this wasn't a fluke. We ran it twice independently and got consistent results. This is a robust directional failure and not noise. The augmentation results are fascinating. For ResNet 50, adding color jitter catastrophically hurts the performance and dropped from 0.82 to 0.03. For VIT, it helped massively, jumped from 0.49 to 0.834. Why? Because VIT learns global patch relationships across the whole image, making it more robust to surface level demographic shift. And for CNNs rely on local textures like skin tone and lighting variation that throws them off completely. And this is what it means in the real world. A model trained on European data deployed in rural India could tell anemic patients they are fine. They are not hypothetical. That's literally what our India to Italian numbers show. The 98% accuracy claim does not transfer. This raises real ethical questions around fairness, transparency, and social impact. The population most in need of affordable anemia screening are exactly the most underrepresented in training data. Cross demographic evaluation needs to become standard practice, not an afterthought. And finally, the three key takeaways are: the 98% accuracy on merged data does not mean generalizable. The failure is asymmetric and reproducible. And domain adaptive augmentation isn't a universal fix. It helped VIT by 70% but hurt Resonate by 96%. The right intervention depends on the architecture, and that's it for the presentation. Thanks for watching.